Welcome to this week's SPCLB cast. We are very honored to have Steve Reinhardt, an engineering manager from Microsoft, who has been, actually, we know each other since a very long time, but Johannes invited him, so thanks to Johannes. And yeah, so Nikolai is going to give an introduction about Steve, and then we can get started right away without further ado. Thank you.
Thank you, Torsten. And once again, thank you, Steve, for agreeing to give a talk at this SPCLB cast. Steve is a partner hardware engineering manager in the Bing Platform Engineering Group at Microsoft. He's also an IEEE fellow and an ACM distinguished scientist. Before his job at Microsoft, he was a senior fellow at AMD Research. And before that, he was an associate professor in the Electrical Engineering and Computer Science Department at the University of Michigan. He has published numerous papers at top conferences and journals, and was also the primary architect and developer of M5, a full system architecture simulator. Without further ado, Steve, thank you. Take it away.
All right. Thanks so much, Torsten and Nikolai, for having me here. And I'm glad to be here. Glad this worked out. So before I get started, just a couple of things. I'd like to acknowledge all of the many people at Microsoft that have worked on this. We've had dozens of people probably working on Brainwave over the years, and if you include everyone else who's been involved in getting hardware into production and stuff, there are hundreds of people behind this work. So I just go to meetings, and once in a while I get to make some slides and give a talk. But this is the work of a large cast. And also, I'll be focusing in this talk primarily on the project from a hardware and architecture perspective. But there's a lot of other stuff we've done on the software side in terms of sophisticated runtime system. We have a compiler, things like that. In the interest of time, I won't be talking about those. But I do want to mention, this is really just one slice of the overall project. So with that, I'll get started. I think the first thing is to kind of clarify where we are in the space, so what I'll be talking about, what I won't be talking about. DNN acceleration, of course, is a very hot topic, but there's a lot of different sub areas within that space. And one of the primary dichotomies in DNN acceleration is training versus inference. And training, I think, gets a lot of the limelight. It's kind of the big hero job, and what everybody wants to aim for. And it's you do a lot of brute force kind of big system kind of stuff there. But inference is also a very challenging and interesting domain. It has a lot of differences with respect to training. And of course, there's no value in training these big models if we can't actually deploy them and run data through them on the fly. And then another major dichotomy in the space is cloud versus edge. There's a lot of interesting stuff going on in IoT, or in doing DNN inferencing on your phone or in your car, or things like that. But with Bing being an online service, we are very squarely in the cloud inference area for this project. So that's what I'll be talking about. So in terms of where we are today with FPGA-based inference, Project Brainwave is our system for scalable low latency inference in the cloud. We do this primarily for Bing and Office 365, so what we call first-party services, internal Microsoft services that require DNN inference. There is some third-party access to Brainwave via a few Azure ML service APIs that you can access that have Brainwave in the back end. But it's a project that's grown substantially, and today, whenever you do a Bing search, that search is going to run some inferences on Brainwave in the back end, and we end up doing millions of inferences per second at peak throughput on Brainwave during the day. And lots of different aspects, extracting features from documents for the purpose of ranking. The page ranking algorithms themselves depend on DNNs. Caption generation, those are the little snippets you see under the links on your page, that give you some context about it. Those are selected by a DNN. Question answering. So, actually some of the earliest DNNs we worked on were for question answering, where if you type a query, sometimes we can provide an answer directly on the results page rather than a link, and that's all DNN driven. And so every query that comes in generates thousands of inferences, and it really adds up. So how did we get here? I think in order to understand where this all came from, kind of have to roll back to the foundation of Brainwave, which is Project Catapult. A number of you are probably familiar with that, but that's where FPGA acceleration at Microsoft started. And this gives a little timeline of Catapult. This project actually started over 10 years ago. The initial Catapult prototype was approved in January of 2011, so a little over 10 years ago. Obviously the work behind that started in late 2010. So there were a number of different prototypes and proof of concepts and pilot projects. And then 2014 is when we kind of came up with what is now the kind of canonical Catapult architecture that I'll talk about a little bit on the next slide. 2015 is when Microsoft made the move to ship an FPGA with every server. So we started accumulating servers in the data center. We have very large number of FPGAs in our data centers now. And then since then, we've actually gone through 2 additional generations of FPGAs, from Stratix 5 and these old machines to ARIA 10 to Stratix 10. And then, we have more coming in the pipeline that I'll talk about. So we actually have 3 different generations of FPGAs in the data center. I think one of the interesting things is the typical hardware lifetime in the data center is 5 years. So these Stratix 5 devices that we started deploying in 2015 are really just now beginning to get decommissioned out of our data centers. So we still have a large number of them. And as I'll mention a few times, I think one of the cool things about this project, about Brainwave, is that even though Brainwave itself didn't start until later in 2016, we are running on these FPGAs that were purchased and deployed in 2015 and still getting value out of them. So let's see here. So one of the key things with the Catapult architecture is what we call a hardware as a service model. And the key thing here is the fact that the FPGAs are directly connected to the network. So this is a diagram of a typical server. We have a couple of CPU sockets. And, the FPGA is sitting here on PCIe, but it's got this direct network connection to the top of rack switch. And because of that, the FPGA can directly inject packets into the network. And then when packets come in from the network, they also go directly to the FPGA. So that means any pair of FPGAs within the data center can talk to each other without any software intervention at all. And that means we can get communication over the standard data center Ethernet network, but at basically wire speeds. And you can see over here, I've got some typical values for round trip latency, and we're talking, single digit to tens of microseconds, because there's no software intervention at all. One of the other key things of this architecture is that we are sitting on the path between the network interface, the system network interface, and this top of rack switch. And this means that all of the traffic in and out of the machine goes through the FPGA. And Azure uses this feature to leverage the FPGA for virtual networking. They can do access control and things like that on packets as they go by. And so this really gives Catapult this multi-use architecture. So there's lots of FPGAs out there that are being used by Azure networking, and then some of them we use for brainwave acceleration. There are other projects that use FPGAs for other purposes. But there's a lot of motivation for why it's valuable for Microsoft to deploy these in bulk, is because they're not just supporting brainwave. There's a lot of other projects as well. So this hardware as a service model is this idea that we have this effectively flat pool of FPGAs in the data center that any CPU can access just by going to the local FPGA and doing this quick hop across the network to any other device in the data center. And there's a number of features to this, that this provides. A key one is that we can expose multiple accelerators to a client. So in a typical system, if you're going to have a local accelerator, you kind of have to decide what piece of your workload you're going to accelerate. But with hardware as a service, we don't have to do that. We can deploy a number of different accelerators on the network, and the CPU can access any one of them that it wants to. And so we can have a variety of different acceleration components within a single workload. We can accelerate multiple workloads. And even within Brainwave, we leverage this for intra-model parallelism. So we can take a large model and we can split it up into pieces and put different pieces on different FPGAs and have a single CPU access those pieces of the model and even send them subtasks concurrently to accelerate the end-to-end model inference task. We can also share an accelerator across multiple clients. One of the things we find is that for a typical accelerator, it's very hard for a single CPU to drive that accelerator at full load. So by having, concentrating the workload from multiple CPUs onto a single FPGA, we can drive up utilization and efficiency of those accelerators. And then we can also kind of decouple the CPU to FPGA usage ratio. So sometimes you'll have CPUs running services that don't need an FPGA, don't have anything that's accelerated. We can harvest those FPGAs remotely and use them over the network without interfering with that local service to expand the footprint of our acceleration platform. So it's turned out to be a very powerful architecture. It's really, kind of a form of disaggregation and, kind of leading the way in a lot of the other disaggregation type of things that we see going on in modern data centers. So that's the Catapult background. So that was in place for a few years before we started looking at DNN inference as an application. And that's when Brainwave came along. So Brainwave started about 5 years ago, maybe a little bit more than that. And at the time, we were focused on Bing. So we're focused on natural language processing. Even today, we still mostly do text-based models for web search and other kind of text-oriented things. Even when on the Office side of things, it's mostly like email, Word document processing, things like that. So we started out with these recurrent neural networks, things like LSTMs. So we were motivated by what does it take to accelerate the critical path of an RNN. And of course, as the name implies, the recurrence in the neural network means you have a state, and then you run that state through a bunch of computation to generate the next state. So there's a critical path here, with this long chain of compute going from one state to the next state that bounds the latency of the inference. And you can see that all of these computations start with a matrix vector multiplication. You're starting with the vector, which is the current state, multiplying it by various weight matrices. And then there's a chain of vector computation, some summations, there's a bias add, there's an activation, there's a tanh activation function here, there's a multiplication, another tanh, another scaling multiplication. So we see this pattern, not just in LSTMs, but actually in a lot of other DNNs as well, where there's some kind of matrix vector or matrix compute, and then you take the result of that and you do a bunch of smaller vector ops for biases and normalization and such. So so that's kind of the focus of the architecture. I'll get into that a bit. One key question in terms of the acceleration, of course, most of the compute is in that matrix vector multiplication. And if you look at what most architectures do to accelerate these kind of dense matrix ops, they're kind of two extremes. If you look on the CPU side of things, you look at AVX or something like that. Vector architectures are the most common thing, and so you get these vector ops. And the challenge with those is there's basically no data reuse. You load a vector, you load your vector operands, you do this element-wise computation, and then you save off the result, and then you go get another pair of vectors. On the other extreme, if you look at what GPUs do and what a lot of other AI-focused accelerators do, they go to accelerating matrix computations. You look at like a tensor core on a NVIDIA GPU. And the great thing about matrix ops is you get a lot of data reuse. You're doing every row times every column. So you get to reuse, all of those data elements multiple times before you have to, go and fetch more data. The challenge with that is if you look at these models, these like RNNs and simple fully connected layers, a lot of times you have a state vector that you're multiplying by a bunch of matrix weights. And so if you really want to leverage a matrix operation, you have to batch these operations so that you can get multiple vectors to run through at the same time. And that is going to increase your latency, which is a critical thing for an online service like Bing. So what we did in Brainwave is we kind of went for the middle ground, and our core operation that we accelerate is a matrix vector multiplication. So we get the reuse on the matrix side, from typically the weights of the model, and we're going to multiply, we're going to actually get reuse out of the vector because we're going to multiply it by all these matrix rows, but we're going to focus on doing a single vector times a matrix so that we don't have to do batching in order to maximize the throughput of the device, or we can minimize the amount of batching that needs to be done. So with that in mind, we're going to focus on matrix vector multiplications. We're going to focus on accelerating initially these RNN type computations. So we end up with this architecture for the Brainwave processor. We start out up here with a matrix vector multiplication unit. This is not to scale. This MVM is actually kind of the bulk of the area on the device. And then, we read matrix tile out of matrix register file, we read a vector operand out of this vector register file, do the computation, and then we get a vector out. Then we run the vector down this data path, which allows us to do additions, multiplications, activation functions like tanh and sigmoid. And for each of these binary operations, we have a dedicated register file for that function unit to get the other operand from. And this allows us to do all of those chains that you saw in that original diagram in a deeply pipelined fashion. So the interesting thing about Brainwave, I think, relative to other teams that have done FPGA acceleration for DNNs, is that we're not actually trying to compile a specific DNN model to the FPGA. We've designed this architecture that's generic enough to support multiple DNN models, but then the specifics of an individual DNN are driven by how we configure the data flow through these function units after the MVM, and what operands we use when we do the additions and multiplications, and all of that's driven by instructions that are sequenced by a control processor. So we have a soft core on the FPGA that's running firmware written in C that's driving instructions into this data path and sequencing these operations, so that within the space of operations that we support, we can customize this to different types of models. So like LSTMs, GRUs, other things like that are very easy to support. And as we'll see in a bit, we can expand this to other types of models as well. So the key concept here is we actually generate a chain of what we call a chain of instructions that sets up the data flow from the matrix vector multiplier through these other operations. We configure this crossbar to sequence these function units and then this other set of function units. Then we do a write back stage where we can write back. We can actually multicast to any of the register files in the write back stage. And once we get that set up, then we can run a number of vectors through that configuration in a pipeline fashion in a direct data flow type of computation. And then as that computation finishes, we reconfigure the data path for another chain of instructions to do another set of matrix and vector operations. And then I'll point out also that we have this kind of bypass VRF here. So if you have a chain of vector ops that doesn't start with a matrix vector multiplication, you can kind of drive directly into the vector data path here as well. So this was our original architecture, very optimized for LSTMs and RNNs in general. The great thing about having an FPGA platform is that it allows us to evolve the architecture relatively easily. So one of the key aspects of the project is that we've been able to evolve over the course of a number of years to support a variety of different model types. And this is great because, as you know, DNNs, the space of DNNs is changing very, very rapidly. So just quickly over here, we started with these large RNNs. We added support for convolutions and image networks. Added a few other things like ability to do embedding lookouts on the device, and then finally we wrapped up, or didn't wrap up. Our last big push, I guess I should say, is doing BERT and transformer models. I'll talk a little bit more about that in a bit as well. So I think the interesting thing here is that because we're able to evolve the architecture on the fly and add features and redeploy onto the FPGAs we have, we can actually ship a lot faster because we don't need to worry about future-proofing the architecture. Anything, if we have an architecture that's kind of good enough for the models we have today, then that's good enough and we ship it because we know if our requirements change, we can update the architecture later. And it also decouples the physical deployment of hardware from the development of the RTL for the architecture itself. So we can, if you're doing an ASIC, you have to not only design the chip and do the tape out and get the devices back, but then you have to build the systems and do the manufacturing and deploy them in data centers. And, as I've learned being here at Microsoft, that always takes longer than you think it should. But with an FPGA-based platform, we can basically design the physical hardware, start the process of manufacturing and deployment in parallel with the RTL development. And then the RTL just needs to be ready when those systems are in the data center. And then, as I've said, even if the requirements change, we can update the RTL. And as I mentioned before, the cool thing about this is we are deploying Brainwave today on these original Catapult FPGAs that were purchased and deployed before the project even started. And we're even running transformers on these, the BERT paper came out in October 2018. It was kind of late 2018. We started getting customers of ours, internal customers of ours saying, hey, can you do this? There were a number of features that we didn't have that we needed to add in order to support BERT, but we did that. And I think by June 2019, we were shipping transformer models in production on this hardware that that existed in our data centers before the BERT paper was even written. So that's a lot of flexibility and power there. Very exciting. And then another aspect is we can actually specialize 4 different classes. So as I mentioned, we've added a number of features to support these different model types, but rather than having that grow the resource requirements of the accelerator directly, what that really means is we kind of specialize. So we have a transformer version of the accelerator, and we have a RNN version of the accelerator and a CNN version of the accelerator, and each of those only has the features that are needed for that class of models. But then within that class of models, we use the firmware running on the control processor to specialize for specific models within that class. So let me now talk a little bit about some of these specializations and enhancements we've done. I actually have a couple of examples I want to go through. The first one is what we call simultaneous multi-chain support. This is the architecture again, just to clear things up. I'm going to get rid of some of these other pieces. They're still there. I'm just getting them out of the picture for clarity. And as I mentioned before, the main kind of computation flow is really going from this matrix vector multiplication through this sequence of dependent, vector operations and into the write back stage. And then if you have additional vector computations, you can go through this second path that I pointed out through this separate vector register file, so you don't occupy the matrix vector multiplier. But what we saw is in a number of models where we had some computations of both types, you run into this structural hazard here, where you may want to do a matrix vector multiplication, but these vector units are busy servicing a previous instruction chain that didn't use the matrix vector multiplication, and then you have a conflict there. So what we did, and in particular in the Stratix 5s, there's a limited amount of resources, so there's not much you can do. But as we get into these newer generations of devices, we have more and more resources, so we can get a little more creative in terms of how we address these bottlenecks. So what we did with this simultaneous multi-chain idea is say, hey, we don't have to share the same vector data path for these 2 types of instruction chains. what we can do is kind of split out this this separate data path for these vector-only instruction chains like this. And now we can actually run two different instruction chains simultaneously, depending on whether it starts with a matrix vector multiplication or not. And so that's where we got this simultaneous multi-chain name from, kind of tongue-in-cheek. And then once we do that, we can further analyze the code that we're running and say, hey, now that we've segregated these instruction chains into these two different types, it's not the case that both types of chains typically need the same types of operations. And so we can specialize the function units to these different types of instruction chains that we see in production. So maybe after the matrix vector multiplier, we only need one of these multifunction units. We don't need two of them, and maybe we don't need a multiplier. And then on the other side, maybe we only need one activation function and one multiplier, but we need two adders. So we can kind of slim down the resource constraints or resource usage a little bit through some additional specialization here. And then once we've done that, if we still have area and we need to improve throughput, we can do that by replicating these chains. So we go through and we can add multiple copies of these data paths, and then have effectively the way we schedule it is we have multiple iterations of a loop can occupy different instances of these data paths for higher throughput. So that's kind of the one optimization side of things. On the functional side of things, as I mentioned before, we had this requirement in late 2018 where people wanted to run transformer models. And one of the requirements that came out of that was that there are a number of vector normalization ops like Softmax and layer norm that occur within each transformer layer. And originally we had a few models that use Softmax at the end, but we could always do that on the CPU. But when you have a multi-layer model and you need an operation in every layer, you can't afford to keep going back to the CPU to do the things that your accelerator doesn't support. So we needed to get support for these normalization ops onto the FPGA. And so we came up with this idea, which we call the Scalar processing unit. Originally in that original data path, all of those vector operations were just element-wise operations, whether additions, multiplications, whatever. So to do these normalizations, you need some cross-vector ops, which we did not support. So we had to architect this new function unit to do that. And you can see here, the nice thing about it is it's got a vector input and vector output. So it integrates nicely into the vector data path. But inside this unit operates on scalar values. And it has a couple of special function units. There's a reciprocal and a square root that you can do on these scalar values. And then in order to go from the vector input to the scalar value that gets operated on, you can select either a sum reduction or a max reduction. And then when you come back out, you can take a scalar and you can broadcast it across a vector, so you get n copies of that scalar. And the interesting thing about this is it's really a fairly simple set of operations, but it's sufficient to do both softmax and layer norm and some variations on them. Whoops, sorry, I went the wrong direction. There we go. So I won't go through this in excruciating detail, but it's kind of interesting to look at how you can take a scaled softmax here and map it to this set of operations that either we already supported or are supported by the SPU. So in the scaled softmax, we first compute the max and offset the vector by the max value so that the exponent doesn't overflow. And so you can see we can do the max reduction to calculate this max value, broadcast it. So now we have a new vector that's replicas of the maximum of the vector, and then just do our existing pointwise subtraction to get this xi minus max. We do a pointwise exponentiation, which is another simple pointwise vector function unit. We had to add it, but it fits in the data path very nicely. Then, we do the sum reduction, we do a reciprocal, we do another broadcast, we do a pointwise multiplication, and boom, we've got this softmax result with several trips through this with this SPU, but nevertheless, it's all done right there in a programmable fashion where we can reuse these same operators to do layer norm and other similar functions as well. So that's kind of the architecture side of things. Let me shift gears a little bit and talk about some of the kind of data science side, and particularly about quantization. A lot of the performance that we get in Brainwave comes from the fact that we're able to aggressively quantize down to very low precision values. And that's a big win in terms of improving the effectiveness of on-chip storage, of off-chip memory bandwidth, and of logic density. For every bit that you save on these multiplies, the amount of logic or on the values, the amount of logic required to do a multiply goes down quadratically. So we have a format that we call a Microsoft floating point that enables aggressive quantization, but minimizes the resultant accuracy loss. And I should add that being able to employ this on FPGAs really enabled experimentation and validation that we might not have been able to do otherwise. So because we could configure the device to leverage different precisions just by resynthesizing the design, we could go to production with, let's say, 3-bit precision, or try to go to production with 3-bit precision. And if that wasn't enough, we can resynthesize the design to a 4-bit precision with some loss of performance, but at least we would get adequate accuracy. Where if you're going straight to an ASIC design, you may not want to bet your tape out on a particular level of precision being adequate. So let me just briefly go over the idea here. If you look at kind of standard floating point values, even when you go to reduced precision floating point values like FP16 or bfloat16, you can see that you're spending a lot of overhead on these exponent bits. So one way to get rid of that, of course, is to go to a fixed point or integer format. And of course, int8 and even int4 becoming very popular in some circles. But then the problem is you've lost a lot of dynamic range, and your accuracy can really suffer. So what MSFP is, it's a block floating point format where we have individual values that are very small, say 4 bits, three manticipits and a sign bit. But then we have an exponent that's shared across a block of values. And that way, if you look at this particular example, which we call MSFP 12, we've got an 8-bit exponent and 4 bits per value with a block size of 16. We're really at 4.5 bits per value here. So we're roughly at the density of int4, but because we've got this exponent field, we have the dynamic range of bfloat16 or FP32 even. And of course, there is some current constraint in terms of the exponent sharing, but nevertheless, it turns out to be a very powerful compromise. So one of the reasons it is so powerful is because it maps very nicely to dot product operations. So of course, doing a dot product between two vectors is a key component of these matrix vector and matrix optimization operations that we've been talking about. And so the nice thing with this block floating point format is if you have two vectors represented with this shared exponent, then you're doing an element-wise dot product on the values completely in the integer domain. So all the multiplications and the sum reduction are all done as integer operations. And then it's only once you've done that dot product that you have to do the floating point normalization between the two exponents. So you're, again, effectively getting close to the compute cost of integer values, but while still having the dynamic range of a floating point. So these are some numbers that we recently had a NeurIPS paper, last December on this. I'll give you the citation at the end, but these numbers are from there. And what this diagram shows is comparing the accuracy that we're able to get for the ImageNet benchmark for different precisions, both floating point, integer, and this MSFP, versus the area required for a dot product, basically. And you can see that, for these MSFP 14, MSFP 16 type values, where we have, this is assuming an 8-bit exponent, so that's 6 or 8 bits of sign plus mantissa, we are getting accuracy comparable with int8 or float16 at a much lower cost. You can see this is a log scale on the x-axis. And then we can even drive that down further. And for something like MSFP12, we're getting nearly the same accuracy at lower complexity than even int4 computation. As I said, it's been great to have the FPGA platform to kind of prove out this idea and give us the flexibility to try it in production, try it with a number of production models, validate that we can get the accuracy that our customers require for the features they want to deploy, but also get the performance that we expect. And so given that experience, we were able to go to Intel and work with them to harden this MSFP format into the DSP blocks of a Stratix 10 FPGA. So Intel announced this Stratix 10 NX family last fall, I believe. And so this is a standard Stratix 10 device, only what we've done is gone and taken the DSP blocks, which I'll talk about a little more on the next slide, and replace them, the standard DSP blocks, with blocks that support this MSFP format. And this allows us to get a lot more throughput because we've hardened this critical logic. And in particular, the standard DSP block here is basically a sort of float 16, kind of mixed precision float 16, float 32 component. And so you get 2 multiplies and 2 accumulates out of that block of logic. And basically in the same area, now with MSFP, we can get 30 multipliers and 30 accumulators going down to the what they call block FP12, which is our MSFP12 format. So the in the same area and the same power, the throughput is much higher now. So we're as I mentioned, we have 3 generations of systems in production now, and we're actually in the process of deploying these Stratix 10 NX devices as our 4th generation of platform for Brainwave in our data centers. So that kind of leads me to wrap up a little bit with some observations in general on this whole path that we've been through over the last several years. Just to recap, there is a lot of skepticism. I know people think FPGAs are too slow or too expensive or something, and everybody wants to do their own ASIC. But there's a number of advantages of using FPGAs. One is that it's not just DNNs. As I've talked about, Brainwave is a substantial user of FPGAs in Microsoft data centers, but is far from the only one. So really the flexibility of FPGAs and their applicability to multiple uses and workloads is what justified the large-scale deployment that started off the whole Catapult project. And then, the flexibility, as I mentioned, allows us to rapidly evolve, to keep up with rapidly changing domains like deep neural networks. We can ship faster because we don't need to worry about future-proofing. We talked about decoupling hardware deployment from RTL development, and in particular, this idea of kind of backporting newer accelerators and newer models onto older devices that are already in the data center, and maximizing the use of these things. If you think about these old FPGAs that we got 5 years ago, if you had bought a dedicated DNN accelerator 5 years ago, I think the probability that it would still be useful today is pretty slim. It allows us to stay lean. We can add features only when they're needed. Again, because we're not needing to future-proof, we don't have to put anything on there that's not needed. We can specialize for different types of models, so we can only put features in for the classes of models that need them. And these are things that allow us to regain some of this performance that we do lose from the configurability of the FPGA device. And then finally, it allows us to do some risk taking. We can try some things out, see if they work, try them all the way into production. And then, if they don't work, we can still, roll them back or tweak them. And so we don't have to take as many big bets on something like a tape out, when we can, validate them in production first, and then move them to hardened logic when they do prove themselves, kind of like with this MSFP format. Just a sec here. So another way to look at this that's, was an idea from my colleague Andrew Putnam, is that if you look at the performance of an ASIC versus an FPGA, people get very focused on this idea that, hey, for a given RTL design, an ASIC is going to be, much more higher performance and better efficiency than what an FPGA is going to be. And that's kind of shown abstractly here on the vertical axis of this diagram. But what happens over time is that if your workload and your requirements change, the applicability of the ASIC may fall off over time, particularly if there's a lot of churn in your workload, where you can reconfigure the FPGA to stay relevant. So after a number of years, the FPGA may actually be giving you better value than the ASIC because you were able to reconfigure it to meet your evolving needs. And in fact, if you look at the design cycle, it's even well, better or worse than that, depending on which side of the fence you're on. The challenge with the ASIC is that you have to start early in terms of planning and architecture and development and tape outs and deployment and things like that. And so by the time the device is in your data center, it's been 12, 18, 24 months since you started working on this thing, since you came up with the initial requirements. And in a fast moving field, things can change in that window. So by the time you have it out in your data center, it may already be beginning to show signs of age. Whereas I've said, the FPGA, you can keep developing RTL right up until, the hardware hits the data center floor. And so, you kind of take this diagram and shift it to the right a little bit and potentially see an even bigger advantage for the FPGA over time. And again, these scales we're talking about are numbers of years. So it's important to be able to take that investment that you've had that's going to be sitting there in the data center for multiple years and make sure that it's still giving you value all the way up to the end. Another way to look at this, kind of a visualization that I came up with, is it's really a question of how do you specialize and how much do you specialize. I think as we've seen, particularly with the Moore's law and Dennard scaling fading away, specialization is really where it's at in the architecture space. And there are a lot of open questions about how do we do specialization right. So if you look on kind of one extreme, we've run on CPUs for a long time where the hardware is really not specialized at all. And all of the specialization for the workload comes from the software that you run on it. And when you move to something like a GPU, you've specialized the hardware somewhat for, let's say, data parallel computations, but you're still getting most of the workload applicability out of the software that you've written to run on this thing. And then we come in from the other end with an ASIC type of device, a true fixed function ASIC, right? Everything is done in hardware. And typically you actually have a more programmable ASIC where most of the specialization is in the hardware and maybe there's a thin software layer for some configuration. And the interesting thing about, I think what we're doing in the Brainwave space and in Catapult in general is looking at some data points in the middle here. Oops. So if you have an FPGA design like Brainwave, the hardware is really not even less specialized than the CPU. It's not even specialized for running code. And then we have some field programmable hardware that takes us a long ways toward the domain that we're specializing for. And then in our case, as I mentioned, we still run some software on top of that to specialize further. You can think of a platform where you're directly implementing a model on the FPGA as being fully specialized in the field programmable hardware part. And then when we look at something like the Stratix 10NX, maybe a little subtle here, but the hardware is more specialized than it is in a generic FPGA because it's targeting these kind of AI, low precision tensor workloads, but still we're getting most of the specialization out of the field programmability and a little bit out of the software. And I think, one of the really interesting questions going forward in the next few generations of hardware is, kind of what's in this gap over here on the right between where we're at with something like a Stratix 10NX and where people building, dedicated DNN ASIC accelerators are at. And so, is there some midpoint where, there's more hardware specialization, but we're still leveraging some field programmable hardware to do some additional kind of medium time scale architecture and specialization, and then run some software on top of it. What is this? Is this the right balance? And what would that device even look like? But I think there's a number of developments, companies, particularly some startups with some interesting ideas in this space. And I'm kind of excited to see where things go over the next several years in figuring this out. So that's all I have. Thanks, everybody. Here's some references. If you want to learn more about Catapult, this Micro 2016 paper really is a very good description of something pretty close to what we actually deployed. We have a couple of Brainwave papers. I particularly recommend this ISCA 2018 paper. It's a little more dated, relative to what I presented here, but it's a good detailed background. As I mentioned, this MSFP data type was just presented in the last NeurIPS. And then, Intel, of course, has more details on the Stratix 10NX on their website. So thank you very much. Thanks for listening. Thanks for having me. And I guess at this point, I'm happy to answer any questions anyone might have.
Thank you, Steve, for the excellent talk. And before we move to the Q&A, just want to mention that our next SPCL BCast talk will be on the 22nd of April, again at 6 p.m. Zurich time, 9 a.m. Pacific, where Mariam Mary Denavi from the University of Toronto will be speaking.